have more exciting topics like this, and we will see more and more participants. And I also welcome all the participants for this presentation on photon counting CT. We are a little bit deviating from the routine radiotherapy topics. This is a diagnostic work, but it has got application in radiotherapy as well. Now, moving on. Presentation on photon counting CT. It's not moving. Oh, okay. So we all know about computer tomography. The conventional computer tomography was invented sometime in the early 1970s, and since then we have seen it being extensively used in the clinical practice. The clinical usage started somewhere around the 1980s, and during these last 4 decades or so, we have seen tremendous advances taking place in this field, and we have seen several generations in front of us, unfolding in front of us, generation 1, generation 2, generation 3, generation 4, and we have come back to generation 3 CTs. Then the spiral CT started in 1990, and about 2 decades ago, we saw the invent of multi-director CT and also the dual energy CT in 2005. But now the technology has reached more or less a saturation phase, and there is no further scope for improvement. It's a kind of mature modality, and no further scope for any kind of improvements. Just to see a quick look at the important parts of the CT, the X-ray tube and the detector assembly, they are assembled inside a gantry, a ring type of gantry. And there are many rows of solid-state scintillation detectors in the form of gadolinium oxide or gadolinium oxysulfide. And there are photodiodes attached at the backside of these detectors. The physical basis of CT imaging is also very well known to us. CT imaging is actually, we are measuring the linear attenuation coefficient of the different tissues. Each tissue has got its own linear attenuation coefficient depending on the density and its atomic number. And the mu is partially due to the photoelectric component and partially due to the Compton effect component in the energy range that we commonly employ in the diagnostic field. What happens is that how we are able to determine this mu is that we take multiple projections around the patient as the CT X-ray tube moves around in the helical fashion. And after obtaining the projections, we go on to reconstruct. And at the end of the reconstruction process, for each voxel like this, we assign a HU value based on the linear attenuation coefficient. Now, when I say matured or there is no further scope for improvement, there are many limitations. For example, there is no further scope for improving the number of detectors. Initially, we started like this with a large sized detector, and then we increased the number of detectors or decreased the size of the detector like this. And now we have got like these many detectors. Currently, there are about 900 detectors in each row. That's the number of detectors in the modern day CT scanners. But we cannot increase the number of detectors beyond a certain limit. That is one of the limitations in CT. So why so? Why are we not able to increase the number of detectors? That's because of the septa. You see here the detectors are separated by a septa in between them. The septa is very thin, actually 0.1 millimeter thick only, and it prevents light from escaping from a detector pixel. So light produced in one pixel cannot go to the other pixel. We don't want that, and that is done by this septa. But as the number of detectors increase, as you can see here, the number of septal layers also will increase. right? Because more the number of detectors, there is going to be more number of septal layers uh, separating the detector, and that means that there will be higher amount of non-absorbent dead space. That is because a photon, if it is falling on the septa, then it is going to be absorbed in that septa, but not going to produce any signal. So it is going to result in wastage of radiation, wastage of the dose. So decreasing pixel size means decreasing efficiency. So we now have about 0.8 by 0.8 millimeter square to 1 by 1 millimeter square. That's the size of the detectors that we have got now, and the dose efficiency is only about 70 to 80%. So the bottom line is that number of detectors in a row cannot be increased beyond a limit. There's no further increase possible. The other problem is the detectors that we use in conventional CT scanners, they are called as energy integrating detectors, or simply called as EIDs. Clinical CT scanners use these energy integrating detectors. Why do they have to use these energy integrating detectors? Let's see the reason behind that. First of all, in each rotation, we saw that the mu is obtained by rotating the X-ray tube and detecting the transmitted X-ray. So in each rotation, there are 1,000 projections from different angles, 1,000 projections in each rotation. Now, the speed of the X-ray tube or the gantry is about 4 RPS, 4 rotation per second. That means per rotation it takes 250 milliseconds. So 250 milliseconds, there are 1,000 projections, because in each rotation there are 1,000 projections. The time per projection we can calculate to be 250 microseconds or 250,000 nanoseconds. That's the time per projection. During this time of 250 microseconds or 250,000 nanoseconds, there are about 30,000 X-ray photons arriving at each single detector element. Each single detector element will see about 30,000 X-ray photons in such a short time of 250 microseconds during that one projection time. That means we have got just about 8 nanoseconds to collect and measure the intensity of each photon. Supposing if our intention is to measure each photon, the signal produced by each photon, then in that case, every 8 nanoseconds, we have to collect that signal and process it, and then make that photodiode ready for next detection. Even the fastest detectors that we are having currently, they cannot keep up with this requirement. So what we do, we just integrate, or we just put all these 30,000 photons together and measure the signal together. So this is what you see pictorially. You can see this is the scintillator, and these are the collimator blades. And you can see here, these are the reflectors or the septa. So X-ray photons are coming like this, they just pass through, and somewhere inside the detector, they interact, produce a light pulse, and the light travels and reaches the photodiodes. There is glue in between the detector and the photodiodes. So there are more number of photons like this, number of photons in each detector element. They keep coming, falling on these detectors, and each detector producing each photon producing light pulses, and these pulses will reach like this. They just expand and then they reach the photodiodes. And the septa function is to keep the light produced in a particular detector element to within that element only, not to allow them to go to the other element. Otherwise, there will be loss in signal. So that is why these septa are reflecting the light back to the concerned diode. So we just put all the 30,000 photons in each detector element. Approximately, there will be more or less, and We just collect all the 30,000 photons together, measure, and that makes the signal. Now, there are problems with this kind of integrating. The problem number one is that in order to reach the detector, suppose you see this X-ray tube, the X-ray photon interacts inside the detector, means first of all it has passed through the filter and then the patient. So to reach this detector, the photons should be of sufficient energy, at least 25 keV or above. Anything less than that will be absorbed simply by the filter and also by the patient. So energy will be minimum 25 keV or above, only then we can reach the detector. And any signal below the 25 keV will be simply nothing but electronic noise. The random noise that is happening due to the detector assembly, the circuitry, and many other reasons. So any signal below the 25 keV is simply the electronic noise. And this is the signal finally that gets detected. How this signal is formed, you can see here. Now one photon is coming, interacting, and that photon light is this much because it has deposited very less energy, so the signal is very small. This is another photon. This is another photon. So you can see here that there are many number of photons producing light pulses, and all these pulses are collectively summed up to form this accumulated signal. This is what actually detected by the photodiode. Summation of all the individual photons, around 30,000 photons here. Together cumulative, they form the signal. Now, within this energy integrating, look at these. These are not due to any photons. These are just only noise happening due to the detector circuitry, electronic circuitry. So within this signal that has been integrated over that 250 microsecond time, 30,000 photons, this noise is also incorporated into that energy weighted signal. So the image quality is degraded. And then we call it as energy weighted. Why do we call it as energy weighted? Let's see why we call it as energy weighted. But first, the energy integrating detectors, the noise, what does it do in these detectors? The low-level analog electric signal of the photodiodes is distorted by the electronic noise. So the noise actually causes a disproportional increase of the it causes disproportional increase of the image noise and an instability of the low CT numbers. So that is problem number one. The problem number two is that we are interested in lower energy photons because lower energy photons only carry most of the information, the low contrast information. While doing CT, we want to differentiate between low contrast materials like soft tissues. We want to differentiate between the low contrast media. So for that, low energy photons are important because only they can actually differentiate between the soft tissues. But then these low energy photons, as you can see here, they contribute less to the integrated signal, which is dominated by the signal from the high energy photons. Look at these high energy photons, they dominate. It's something like in a class, you know very well that in a typical school class, there will be always some 2 or 3 bullying personalities. They will bully the soft speaking, good people. They will just suppress or they will just overshadow them. So these high energy photons, they actually suppress these low energy photons. The signal coming from the low energy photons, they get actually buried in the light of these high energy photons. So it leads to energy weighting. By default, it leads to energy weighting. Means that, for example, after iodine administration, the highest absorption occurs just above the 33 keV, its kh. But these photons, they are downweighted in the signal. So what we have to do, we have to administer more iodine in order to see iodine in the image. So the iodine burden to the patient is now more. So the low contrast information is lost in the presence of this dominating high energy photons. That's problem number 2. So this is what the third problem is that, as you see here, X-ray photons are coming here, they get converted into light, and then the light is the one that actually finally leads to the signal that we measure. So X-ray energy is converted into electronic signal, and that is a two-step process. X-ray photon is there, light is produced, and then electrical signal. What is the problem with this? The problem is that even though the CT detectors have a good quantum efficiency of greater than 90%, the scintillators just convert only 10%, around 10% of the absorbed X-ray energy into light energy. So the rest of the energy is lost. So the light efficiency is less. That means radiation dose is high. So then came dual energy CT, as we had seen in the first couple of slides, sometime around 20 years back. The dual energy CT came, and the dual energy CT employed a different type of technologies. Either they had two X-ray tubes, dual source, or fast kV switching. Means only one X-ray tube, then they will switch between low kV and high kV. Or dual layer detector. The detectors are quite deep, and two different layers will detect two different energy photons. But whatever be the technology employed, ultimately this dual energy CT is used for different type of usages, like material differentiations. In kidney stone, you can characterize the kidney stone whether it is due to calcium or some other effect. Calcium means you have to break those stones, but if it is some other stone, then by medication you can cure it. So characterization of the kidney stones is possible by means of material differentiation, or differential diagnosis of gout. You can do that. Similarly, improved visualizations means you will be able to increase the contrast in the lesions using what is called as the virtual monoenergetic images. We know that in diagnostic we employ a spectrum of X-ray photons, but you can actually virtually create monoenergetic images using this dual energy CT, and similarly you will be able to quantitate, in the sense that if there is a contrast medium in the patient, you will be able to compute what is the what is the concentration level of that contrast media, and then you will be able to show iodine maps. Moving on to photon counting CT, the first biggest advantage of photon counting CT is that photon counting detectors, which are also called as PCDs, they do not go through this two-step process of first X-ray energy getting converted into light, and then light to electrical signal. So there is no two-step process. It is direct conversion of X-ray energy into signal, and they do not require photodiode. There is a single thick layer of 0.9 to 3 millimeter thick semiconductor diode, maximum about 3 millimeter thickness, and these semiconductors are made up of either cadmium telluride, CDTE, or cadmium zinc telluride. One manufacturer, I think GE, uses silicon also, but most of the other manufacturers use this cadmium telluride or cadmium zinc telluride. Now, talking about these crystals are very difficult to grow because of many reasons, because there is need to keep absolute purity while growing these crystals, number one. Number two, crystal perfection. You need to perfectly grow that you have to make sure that the electrical property of the crystal is not altered. And all these material substances are toxic. So you have to create a very special lab. Handling them becomes extremely difficult. You have to take a lot of precautions. And overall, in every step in the process, it becomes a challenge to make these diodes. So this is how actually the detector looks like. The detector is a single crystal. You see here, there are no septors, nothing. Just one single block. And on the top of that, you can see here, there is a cathode. On the top, entire top, there is a cathode. Single cathode covering the entire surface. And there are collimator blades like this. And X-ray photons like this, they come, interact inside the detector, and they produce what are called as the electron hole pairs they produce, and these are then collected, the electrons are collected by the anode. But the anode are pixelated, means they are not continuous like the cathode, they are like these. That is one pixel, this is another pixel, this is another pixel. So these anodes are very small in size, and actually these anodes actually help to produce the best possible resolution. So that's one pixelated anode. So there is a potential difference of about 800 to 1000 volt that is applied between the cathode, which is on the top of the detector, one single cathode on the entire detector crystal, and then pixelated anode on its bottom. That gives the resolution to the detector. The resolution can vary anywhere between 0.11 by 0.11 millimeter square to 0.5 by 0.5 millimeter square. Now, the absorbed X-rays produce, as I said, electron hole pairs, which are then separated in the intense electric field, and the electrons drift towards the anode, and they induce short current pulses in about 10 power 9 seconds, that is in 1 nanosecond. But even though the current pulses are produced in just 1 nanosecond, the pulse shaping circuit transforms them into voltage pulses with a full width half maximum of about 10 to 15 nanoseconds. The pulse height, very importantly, is proportional to the energy E of the photon. The larger the energy of the photon, the larger is the height of the pulse that is produced. The pulses are counted if they exceed a threshold of T0. That is, we are going to see in the subsequent slide what it is and how does it help. But remember, these steps are the ones that are actually helping us, or that determine the supremacy of the photon counting CT over the conventional CT, because these have got the capabilities to resolve the energy. So here is the collimator blade, just like in the energy integrating detectors, but just below the collimator blade, you have got the cathode, and that is the cadmium telluride semiconductor, about 3 millimeter thickness at the most. And just below the detector, you can see that is the pixelated anode. That's one pixel, that is another pixel, that is another pixel, like that. And then the signals are detected by these anodes. So in the energy integrated detector, you can see here there is no more septa, there is no more dead space, and there is very much increased efficiency if we compare against this energy integrating detector. So here one photon comes, it interacts, produces electron hole pairs, and these electrons are moving towards the anode. One single photon is counted by this anode. So that is why the name photon counting CT. There in the conventional energy integrating detectors, we are just integrating 30,000 detectors, 30,000 X-ray photons, and then the signal is a cumulative signal. But here, every single photon, incoming photon, is producing a distinct signal. So photons keep coming like this, and every single photon as shown in this picture, you can see they get counted, the signal is produced as the electrons reach the anode. So in energy integrating detector, we are putting together about 30,000 photons, making the signal, but here each photon gives us a signal. Now this gives immediately a distinct advantage. As you can see here, this is the time as we are detecting the signals, and this is the pulse height in keV. So you can see 730. Threshold is set at 25 keV. So the counting is done only when the threshold is exceeded. If the energy is less than that 25 keV, we had earlier seen it is due to the noise in the circuitry. So those signals are not counted. So the signal pulses are only those which are exceeding this threshold. The electronic noises are very easily, completely stopped from being included in the signal. So the low amplitude baseline noise does not trigger counts. So all these things do not trigger any counts at all. So this is how it works. The side view, you can see here the detector side view. X-rays are coming, producing the electrons hole pairs, and the electrons move towards the pixelated anode. You can see the pixelated anode here, and then they produce the signals like this. And this is the top view, looking from the top. So you can see the crystal, but then due to the presence of the pixelated anode, it is the potential subpixel structure you can see here from the top. That is one anode. You see? So that is one anode, and that is about 0.1 millimeter by 0.1 millimeter square to about 0.5 by 0.5 millimeter square. Now, the signals from these are processed, and you can see here the baseline noise, they are not counted, and only when the signal exceeds this threshold level, then they are counted here 5. So there are 5 pulses exceeding this T0, 3 pulses exceeding this T1, and 2 pulses exceeding T2, 1 pulse exceeding this T3. These are different energy bins. So the values of these 25, 50, 75, 90, all these are user selectable. So X-ray photons are registered during the projection. So during each projection, all the photons that are registered, they contribute equally. Remember in the energy integrating detectors, the low energy photons which carry the maximum diagnostic information, particularly the low contrast information, they get subdued by the high energy photons. That is because high energy photons, they produce the large part of the signal, and hence the low energy photons, they get buried in them. So there is an energy bias. But here, there is no such energy bias. All photons contribute equally to the measurement signal, regardless of their energy. There is no downweighting of lower energy X-rays. So that means there is enhanced contrast, and we don't have to administer iodine much more. We can reduce the iodine administration. You remember, iodine many times is not suitable for patients, and in a way it is toxic also. So this is how it works. There are now 4 signals, 1, 2, 3, 4 signals, and subtracting the detector signal results in the energy bin data. How does it work? You see here, greater than 25 keV, as I had shown, 5 counts, greater than 50 keV, 3 counts, greater than 75 keV, 2 counts, and greater than 90 keV, 1 count. Now, the energy bin, 25 keV to 50 keV, there are 2. 50 keV to 75, there is 1. 75 to 100, 1, and 90 keV, 1. So total 5. So you can see here. So this is how the energy bins work, and the incoming X-ray photons, as they are detected, the counts are allocated to the respective energy bins. Now this is the most important information that the spectral photon counting CT it can give, and this is where the advantage of the photon counting CT is lies in. So you can see here once again energy bin 1, 2, 3, 4, and you can see different counts belonging to different energy bins. And here, as you can see, the energy spectrum, these are K edges, and these can be effectively utilized by selecting the proper energy bins. You will be able to just focus only on the K edge of the spectrum, depending on what material that has been administered to the patient or what you are looking at. So simultaneous readout of the CT data in different energy bins, as we had seen in the previous slides, so it opens up a potential of spectrally resolved measurements, just like in dual energy. So we will be able to differentiate between the materials, and this enables what is called as the multi-material decomposition under certain preconditions. So we will be able to divide a material in terms of two different materials. We will see a little bit more on that. Dual energy applications are mainly based on decomposition into two basis materials. Dual energy applications are mainly based on decomposition into two basis materials, iodine and water or iodine and calcium. See, like if you are using only one single energy, there are two materials, material 1 blue and material 2 red. Now, if you are using a single energy CT, like in the conventional CT, at this point, we are determining mu of a particular voxel, and two different materials can have the mu, same mu. But we do not know that whether this material is this material 1 or material 2. Both have the same mu at that energy. But then when you do dual or multiple energy, like just now we are seeing, we can categorize them into different energy bins. Then mu will not be same. As you can see here, the mu of red is higher than the mu of blue, but then here in the higher energy, the mu of blue is higher than the red. So the mu will not be same, and the tissues can be differentiated. So all spectral technologies are based on this decomposition theory. So they use measurements of the same object, the same voxel, with two photon energy spectra. So this decomposition theory prescribes a method to convert the two measurements into two universal energy dependent physical phenomena, referred as basis functions or the two-base model. And what is the advantage? The advantage is that you will be able to describe the attenuation of material as a linear combination of two basis functions, which gives additional information about the material. So attenuation of a material can be described as a linear combination of two other materials. So it helps us to better quantify and visualize whatever that we want to see. So you can see here, this is what happens. Mu or mu by rho, whatever it is, linear attenuation coefficient or the mass attenuation coefficient, it can be divided into this. So this mu or mu by rho is dependent on two factors. One is material dependent and another is energy dependent. So this is material dependent, this alpha and this one. So there is a photoelectric component. We know that a mu, linear attenuation coefficient or mass attenuation coefficient, part of is due to the photoelectric effect P and part of is due to the Compton scatter C. Now each of this is material dependent and also energy dependent. So this is the form we write, that mu by rho, there is a photoelectric component and there is a Compton component, and within that we can see that there is a material dependent term and there is an energy dependent term. So if we image at two different energies, one at low energy and one at high energy, so we can write these equations like this. And these energy dependent terms are easily known from the measurement and also from the published data. So we can solve this equation to determine this alpha P and alpha C, which are the material dependent terms. Once alpha P and alpha C are computed, then they can be recombined artificially to recreate different types of spectral image. We are going to see what kind of images that we can produce. There is another way of expressing this mu by rho or mu. We can express the mu by rho or mu of a particular element in terms of linear combination of the mu by rho of two different media 1 and media 2. So M1, M2 are shown here. So this is called as the basis material model. Attenuation of any material can be represented by a linear combination of two basis materials. Please refer to these papers, and there are many other papers, books. This is a book and this is a paper to know more about these mathematical terminologies. But the goal of this material decomposition process is to find the best linear combination of two base functions that describe the attenuation of a material. So to pictorially describe, this is what it happens. You see here, you can refer to this book also, The Spectral Photon Counting Computed Tomography by CRC Press. So here you can see the attenuation coefficient of different tissue types that are found in the human body: water, blood, fat, cortical bone, vertebra, and also the contrast media, 15 milligram per milliliter iodine in the blood. So these are the unique attenuation curves of these different substances. Now look at this here. This violet, that is 15 milligram per ml iodine. This violet with the KH, that is this iodine. And this green one, that is the attenuation curve for the water. Now, here you can see this gray, that is the vertebra. See this gray one, that is the vertebra. So vertebra. So the vertebra can be expressed as a linear combination of this iodine with water. So you combine them in the proper ratio, a proper linear combination at two different energies, then you will be able to reproduce this vertebra curve. So you can see here, that's the vertebra curve. Except for this KH, you are able to almost reproduce by proper linear combination of these two base materials. So here, iodine and water are the two base materials. So similarly, there are different types of base materials that are usually chosen in the diagnostic application, either iodine and water, or calcium and water, or iodine and calcium, like that. Similarly, you can break them into photoelectric component and the Compton effect component. Now that's the vertebra, the gray line you can see here, that's the gray line. And here you have got the photoelectric component of water. This is the vertebra attenuation coefficient. Here is the attenuation coefficient of water, but only the Compton component. And this is the attenuation coefficient of water, only the photoelectric component. By adding these two or combining these two in a particular linear proportion, you are able to reproduce this violet curve. A into Compton scatter, water Compton scatter, plus B into photoelectric effect will give or will duplicate this vertebra. So the thing is that the basis of the decomposition process is to find out the best linear combination of two base functions. So what are the applications? See this dual energy ratio. So materials such as iodine, calcium, uric acid, soft tissue, and water can be accurately identified by their known dual energy ratio, right? So you can see here, iodine, you see these are HE values, CT value, HE value at low kVp, CT value at high kVp. Whatever be the energy, high kVp or low kVp, air has got minus 1000. There is no 740 variation in that. Water, whether it is high kVp or low kVp, water has got always 0. There is no variation in that. But look at iodine, low kVp. It goes without saying, iodine 33 kV kH. So it will have a very high CT value at low energy. Look at this low kVp, its value is very high here. Very high, much above 0. But in high kVp, the same iodine, it has got slightly above 0. So this is what we call it as dual energy ratio, DER. So this DER is 2 for iodine contrast, and for calcified bone it is 1.5. So by looking at this DER by this graph, or you can see here also, you can see this is iodine at different concentration level, 4 milligram, 10 milligram per ml, 15 milligram per ml, and similarly calcium, 50 milligram per ml, 100 milligram per ml, 300 milligram per ml. So they produce distinct slope, and using the HU that you have measured at one high energy and one at low energy, using our bins, we can easily know this HU value at low kV and at high kV. So we will be able to find out what are the materials. So it will be able to, we will be able to differentiate iodine from calcium and from bone. So you can combine the images after the reconstruction in different ways. So you can first do the reconstruction, and the reconstructed images can be blended in different ways to produce simple blended image, to produce iodine map, and also to produce what is called as the virtual non-contrast image. You simply subtract the iodine and you will get a virtual non-contrast image. What does that mean? That means you don't have to see, like now what we do first before administering iodine, we take we do a CT scan, and after that we administer iodine and we do another CT scan. So 2 CT scans we do, but then using this, we just simply do an iodine map, subtract it from the original image, and we can get virtual non-contrast image. And we can combine them using the material raw data before the reconstruction, and using that we may be able to produce what is called as the virtual monochromatic image, as if the image has been produced using we are using a polychromatic beam, but if you are using a monochromatic beam, how does it look like? So you will be able to produce this virtual monochromatic image, spectral HU curve, material decomposition, effective atomic number, electron density, and various applications you will be able to produce. So simply think, you can see here, that's the water cylinder. I'll just explain with some few pictures. So you can see this water, and inside the water there are 2 insets. This is gadolinium and this is iodine. 2 material decomposition, I said water and iodine. So 2 material decomposition, this is water mapping, and the water mapping easily avoids gadolinium and iodine because the contrast is too high. So it just shows only the water. And this is iodine mapping, water mapping, iodine mapping in 2 material decomposition. The second material is iodine. So iodine, it says gadolinium is also, this gadolinium is also iodine. So like that it tells us. Now, if you add KH imaging, the third differentiation. So third differentiation, you have to use the KH. So water map, once again, it shows only the water. Iodine map, it's a magic. It just simply discards gadolinium and it tells this is the iodine map. And we say gadolinium map, then it tells only this is the gadolinium. Iodine, it completely suppresses. So this is how we are able to differentiate between the different contrasting agents. So once again, another application, a real patient you can see here. Now, the two materials are fat and argon. So fat, the HU value at low kVp and the HU value at high kVp, and similarly for the argon, the HU values at low kVp and high kVp. This is the two material line. Now, if we inject iodine, then the iodine will increase along this concentration line. So iodine has got a very well known slope. As you increase the concentration, it will just move along this line only, parallel lines. So here we take this particular small voxel and we measure. And what is the HU value at low kVp and what is the HU value at the high kVp? And that is the value here. HU value at the low kVp and HU value at the high kVp. So it is somewhere here. And if we back project onto this organ, we can get the virtual non-contrast image. So this is how the virtual non-contrast image is produced. So from here, there is some amount of iodine there. We put it here, and after placing it here, we just back project it along this known slope to find out how it will look like in the absence of contrast. So 3 more examples. You can see it's a 3D printed model, and that is this. I'm not able to see what is this. So you can see green calcium, and I think this is iodine or gadolinium, whatever it is. So different liquids are kept in these in this 3D printed model, and you will be able to differentiate between calcium, gadolinium, and iodine. And similarly here, iodine and bismuth. You can see here, this is the non-spectral model. This is the conventional CT. This is the conventional CT. So you just see the contrast medium, but you do not know what is iodine, what is bismuth. And once you do the material decomposition, you can very clearly see that this is the bismuth and this is the iodine. And similarly, this is non-spectral, means conventional CT image of a human heart sample. And you can see here in the blood vessel, when you magnify, you see there is a whitening. So you do not know that whether it is due to calcification or whether it is due to any kind of blockage. So the material decomposition tells us that there is calcification, and also this is the iodine flow through the vessel. Once again, the same principle, you can see here, iodine 15 milligram per ml, 25 gram per ml. This is iodine, this is iodine, this is tungsten, this is gold, yttrium, and bismuth. 80 kV, threshold 50 kV. So this is low, less than 50 kV. This is just above 50 kV. Now, for all these materials, gadolinium, tungsten, iodine, bismuth, and yttrium, you have got these attenuation curves. So these are the mass attenuation coefficient curves. And now what we did was, we imaged at 80 kV, threshold we set 50 kV, right? So we imaged at 80 kV and threshold we set at 50 kV. So 50 kV, you can see here, this green, that is the gadolinium. So you can see here, this is gadolinium, and here threshold is low, less than 50 keV, so gadolinium is not seen that with good contrast. But once you set the threshold 50 keV, suddenly the KH photons, here is the KH, are taking part, and hence it looks brighter. And similarly, here you see this one, yttrium. Yttrium has got, where it is, this is 61 keV. And this is 70 keV, the tungsten. So this is tungsten, this is yttrium. Once you set the threshold at 61 keV, the yttrium and the tungsten, they become brighter. Another good application is that now if you want to do liver study, conventionally you have to do two imaging. One in the arterial phase. You inject, and from certain time, after few seconds, at a particular time which coincides with the arterial phase, you have to do one imaging, so that imaging will look something like this. You can see here in the artery the contrast is present. And then in the portal phase, when the blood enters the liver, then you can see here the liver is in good contrast, that is the portal phase. You have to do another imaging. So with the conventional CT, you have to do one imaging at the arterial phase and one imaging at the portal phase. But what happens with the spectral photon counting CT? We inject one contrast agent, that is iodine, and after a certain time, we inject contrast agent 2, gadolinium. And we do only one imaging here at this junction. When this is at the portal phase and this is at the arterial phase. So, contrast agent 2 is at the arterial phase, contrast agent 1 is at the portal phase. You do one imaging, and by carefully setting your thresholds, the energy bins, you set one around 33 and you set one around 50.2, then you will be able to capture very nicely the gadolinium and also the iodine. So material specific KH imaging, this is called as material specific KH imaging, and dual contrast imaging, iodine and gadolinium. It looks like this. Conventional image, it looks like this, but gadolinium image, you can see here where the gadolinium is present and where the iodine is present at the portal base. So now, whatever applications that we have seen so far, most of the applications, the dual energy CT, which was invented about 2 decades ago, you can do all these applications with the dual energy CT. That is, there is no doubt about that. Whatever that we have seen so far, we can use dual energy and we can do, or we can perform those tasks also. However, we have to keep few things in our mind. One is dual energy CT uses energy integrating detectors. So whatever problem that happens, yes, that is there, energy integrating detectors, and it involves a two-step process as we had seen in the beginning. X-ray photon is first converted into light, and then light is only detected to produce the signal. And it needs dual exposure, as we had just now seen. Dual energy, you have to expose the patient twice, one at low energy and one at high energy. That means that radiation dose is an issue. What are the clinical applications? So you can see with the energy integrating detector, you can see the sinus CT, how it looks like, and with the photon counting CT, the same sinus with half of that dose, 0.012 millisievert, 0.0063 millisievert. How clarity it looks like, the resolution, everything is good. And similarly, you can see here, this is the conventional imaging the edges are not very well defined, but here the edges are very well defined. And you can see here the calcified coronary artery with iodine in the lumen. So we do not know what is calcium and what is iodine, but PCCT helps us to differentiate. Oh, that is the lumen. Calcium has been removed from the lumen, and you can see the iodine flowing within the vessel. And this is the smallest bone in the human body, and that smallest bone you can clearly visualize in photon counting CD, not in this energy integrating CD. Once again, you can see the differences between the 45 keV, 55, 65, 190 keV. 190 keV, it looks like you can see that it's a non-contrast image. And here you can see the contrast image. So you have not done two imaging, but then by producing these virtual monoenergetic, you can consider this as the contrast and this as the non-contrast imaging. So two mangoes in one stone. Same way, you can differentiate between iodine, gadolinium, and bismuth. Different color coded, artificially color coded, but this is how you differentiate between different media using 4 energy beams. Because of the very small pixelated anode, you get ultra high resolution, so you can see the difference in the standard resolutions that we see in the conventional CT versus the ultra high resolution that is possible with the photon counting CT. Similarly, the stent in the coronary vessels stent has been placed, and with the photon counting CD, you can very clearly visualize the stents and move on to reconstruct the stent in a three-dimensional mode. We had seen similar pictures. And finally, these are the different manufacturers: Canon, GE Healthcare, Philips, Mars, Samsung, and Siemens. All of them employing different kind of detectors, except GE, which uses silicon. Silicon is good, but the thing is that it has to be thick, about 6 millimeter as compared to the 2 to 3 millimeter, which the other manufacturers are using. And it has got certain other problems as compared to that this cadmium telluride and cadmium zinc telluride. So these are the examples of the different manufacturers, how they are approaching. But this is a fast developing area, and in fact, just about a month ago, Siemens came out with a very new model in this one. They introduced another alpha model using this PCCT. In this modern world, nothing is perfect. Just when we think that PCCT or the photon counting CT is the best one that we can see, this is the perfect one that we can see in imaging, then we just realize that there are problems, there are multiple problems associated with this technique. Let's see some of the challenges. The real world PCDs are different from the ideal PCDs, right? Whatever that we have seen, they are ideal PCDs, ideal performance, but real world is much different from that. So the performance is degraded due to many effects. There is something called as what is called as the crosstalk. Now, ideally, a photon that is falling on a particular or at a particular spot just above a anode, pixelated anode, it should just produce only one signal in that detector element defined by the pixelated anode. But actually, it may trigger a count in more than one detector, not just in that detector element directly below the interaction spot. It can produce counts in multiple detector elements adjacent ones due to production of the characteristic X-rays. So, characteristic X-rays will be produced, and those characteristic X-rays can travel some distance from the interaction spot to produce another count in some other distant detector. Or Compton effect, especially if you are using silicon, this Compton effect is there. So due to Compton scatter, the scattered photon can go to a different spot and produce another count which is not wanted or which is noise. They are different physical processes, but they result in photons being counted, as I said, twice in two different detectors with incorrect ranges. So not only that they are producing, one photon is producing count in two different detectors, but the energy detected both in the original detector and also in the distant detector will be not the correct one that we want. So this is what it happens. The K escape, it can go to another a detector element produce a count there. So the energy determined by here, this particular element, detector element, will be E minus E fluoro, the energy escaped from here. And this one will just only count it as E fluoro. So this is one type of crosstalk, and there is another type of crosstalk. The photon is observed close to the border between two detector elements, and part of the charged cloud may extend into a neighboring detector element, and that detector also can register part of the photon energy. So result, a single photon is counted twice, incident detector and its neighbor with part of the energy. So you can see here, this is the X-ray photon interacting and producing a charged cloud. Now, as far as actually this part is here, then it will be collected by this pixelated anode. But when they are very close to the edge of two adjacent pixelated anodes, then part of this electron cloud will come here, producing a signal half of that, and another part will go to this anode, producing another signal here. So, if incoming photon is 50 keV, 25 keV will be recorded here, 25 keV will be recorded here. I am just giving an example. So, it is not correct. So, this is another challenge. So the crosstalks like this, whatever that we have seen, degrade the image quality in several ways, deteriorate the spatial resolution, blur the image because photons are registered in the wrong location, and it may lead to a photon being counted more than once, causing contrast to noise ratio, deterioration in the contrast to noise ratio. Degrade the energy resolution of the detector, reduces reliability, causes noise in the material selective images. And if you can increase the pixel size, you will be able to reduce this effect. It will improve the spectral separation, and boundary effects and the K escape will contribute less to the signal. But the problem is that the maximum size of the detector pixels is limited by the finite width of the full width half maximum of the pulsar, which is greater than 10 nanoseconds. So as you increase the size of the pixel, even though you will be able to reduce the crosstalk, the problem is the full width half maximum will increase. So there will be another kind of problem. What is that problem? That is called as the pileup. So medical CTs, they operate at a high X-ray flux, leading to what is called as the pileup. Up to several hundred million photons per second per millimeter square. That's the number of photons striking at the detector element. So large pixels, then there will be too many photons hitting them too closely in time, and they will be counted as one hit. We will see pictorially in the next one. And sensor material must be fast enough to transport the released charges. Otherwise, it will take long time to read out, and that will actually lead to more pileup. So readout electronics must be fast enough to count the resulting pulses, and if the photons arrive too fast, the resulting pulses will superimpose the phenomenon called as the pulse pileup. So this is what actually That is one pulse. Before it is counted and the detector is made ready for counting another one, another pulse arrives. So together they are summed up, and this is what are called as the pile up. So they should be differentiated. That is the full width, the half maximum. Perhaps the biggest challenge, why are we not seeing this photon counting CT in routine use in clinic is perhaps the biggest challenge, I think, is the cost factor. It can be anywhere around 40 crores Indian rupees, maybe more than that. So to summarize, energy integrating detectors that we see in our conventional CT scanners, they lead to several drawbacks, several type of issues, and there is no further possibility for any improvements happening in the CT scanners, conventional CT scanners. You can say that they have reached a saturation phase. PCDs, they offer several advantages. Photon counting detectors, they offer several advantages. There is no intermediate step. There is increased efficiency. There is very low dose to the patient. And we can completely eliminate the electronic noise, producing that by stability in the low CT numbers. And equal energy weighting. There's no more biased weightage. Every photon has got equal weightage, which means that we will be able to have improved contrast to noise ratio. And we will be, most important thing is that we will be able to do multimaterial characterization. And with that, we'll be able to do a lot kind of image manipulations in order to see what we want to see. Thank you very much for your attention. And I'll be very happy to take the questions. Thank you.
Okay, thank you very much, Dr. Ganesh, for such a lucid presentation. And it was very clear that we got to know all the advantage of the photon counting CT in comparison to the conventional one. So really thank you very much on behalf of AMPI and CMPI to be the first speaker for the CMPI webinar for this year.
Thank you.
Thank you. Shall we, Ganesh, you are able to see the text, or shall I read it out? Venugopal and Saju had written a text.
Yes.
Venugopal has written, what are the major cost drives for PCCTs, and how do these costs compare to the conventional ones?
So I have just stated that it's about 40 crores. So 40 crores versus perhaps about 4 crores or something like that. Are there any cost-effective approaches to implement PCCT technology in clinical settings? I think it is an evolving technology, and perhaps in the coming years we will certainly be able to reduce the cost, but I do not know what is the cost now. Can photon counting method be used with cone beam CT? Oh yes, of course. Yes, we will be able to use. If you remember, there is a flat panel detector. There is a review article. Actually, I wanted to put. I forgot two things. I have forgotten. One is this is a good question. I have seen in the excellent review of the flat panel detector. They have clearly mentioned these two technologies, means X-ray photon to first to light and then light to signal, and X-ray photon directly causing the signal. But they have mentioned that that technology, even though is there, it is not implemented due to the cost factor. But if you can produce a flat panel detector as mentioned in that review article, yes, we will be able to use this photon counting CT with the CBCT also. Will it help for metal artifact detection? Oh, yes, very much. Okay. Once again, we will be able to selectively reduce this metal artifact detection by various ways. Regarding the characteristics X-ray from the cadmium telluride, we can always neglect the characteristic energy X-ray from the cadmium telluride by setting the threshold to not count the X-ray energy. That is fine, but still the initial energy that will be reduced. So it is a challenge. because once the characteristic X-ray is produced, so that one will be reduced. It will not be of the real height.
Okay.
Any other question from the YouTube? Somebody monitoring YouTube?
Yes, sir. No, there are no
Niyaz?
question.
Okay.
Yeah.
No question on YouTube.
How many were there in YouTube?
Around 15 to
Yeah.
18.
15 to
Oh.
20. Yeah.
Okay.
Yes. Now 11 are there.
Okay, that's great. And thank you, Dr. Ganesh,
Thank you.
as well as the CMPI team, Niyas and Arvind and Satish. And I thank all the audience who has participated and taken time to listen to this very interesting talk by Dr. Ganesh. Thank you all.
So next year,
Yeah.
next month, we will have another lecture by
Yeah.
Dr. Ravi Kumar.
Yes.
Yeah.
So we would like to have it in every month from here onwards.
Yeah.
Yes.
Yeah.
Thank you all.
Thank you.
Thank you, sir.
Thank you all. We are closing it now.
Thank you. ചോട്ടി കഴിഞ്ഞിട്ടോ Yes, sir. Yeah. Thank you so much. You've done it very well. Done it very well.
Only thing it took like time little bit.
Yeah, 5-10 minutes extra. That's all. But it was nice. I enjoyed it.
Okay.
And I think sometimes 60 plus came in Zoom itself, and around 20 in YouTube. Mostly like 90, 85, 90 were sometimes. Then it was like some went out and other games like that.
Okay.
60 means then it came like 50, then it again went to 60. That means the different people are coming.
Okay.
Oh, it was nice. Very good. You are tired, na? 1 hour. Tired.
No. The topic I made it clear. Na it was.
Yeah, it was nice.
understandable, no?
Yes, very good. Very good topic. Because it's a very new topic.
Yeah.
People are not knowing actually. The people who attended might be there. Actually, they wanted to be like interested people only. Many of the people, I think so. Because a few people asked questions also. 2-3 people are asked some questions. Nice only. Dr. Dinesh, he was also watching. He just messaged me something now. He was there in the list, this thing, Zoom. Okay, sir. Right. Thank you. Yes, sir. Okay. Thank you. പോവാ അപ്പം എൻ്റെ കഴിഞ്ഞു. ഫുഡ് കഴിക്കണ്ടേ? എന്താ കഴിക്കുക? എന്താ വാക്ക് വേണ്ടി? ചിക്കൻ ഇപ്പോൾ ഒരു പീസ് തന്നില്ലേ? എന്താ കഴിക്കുക പറയണേ. ഈശ പറഞ്ഞുണ്ടാ.
अच्छा very you will have to briefly stop sharing the screen and show you. Is it required like that?
No.
Recently, I had to review a paper
Sized detector, and then we increase the number of detectors or decrease the size of the detector like this, and now we have got like these millimeter iron in the blood. So these are.
Can we start?
how many have open?
30 plus.
Should we?
Yeah.
Okay, please.
Time 7 o'clock. No?
Yeah,
we will start.
Good evening, all. So, welcome to the lecture series, web lecture series of College of Medical Physics of India. I am Dr. Niyaz, Secretary of CMPI. Would like to invite all of you for this webinar, which is going to happen on a fascinating topic of photon counting CT. Today we have our chairman of CMPI, Professor K.J. Mariadas, who is going to moderate this session. So I'll just hand over to Dr. K.J. Mariadas. Please, sir.
Thank you, Niyaz. Good evening, all of you. I am excited to
3 bullying personalities.
Pore.